Hello everyone, I am Aswani, Assistant Professor, Department of CSE AIML at MLR Institute of Technology. Today we will discuss one of the major topic in AI, that is game playing. Let's see the overview of the presentation. Introduction of game playing, NIM game problem, one of the major problem, and examples of the game playing or min-max algorithm. Let's see the introduction. So in game playing, I already said it is a major topic of AI. It requires intelligence and has a certain valid defined states and rules. So here we'll have sequence of choices where each choice is made from a number of discrete alternatives, and each sequence ends in a certain outcome. Every outcome has a definite value for opening play, which means there are two players or two teams will play a game. Ultimately, the end of the game is either winning or losing or draw the game. Okay, let's see. Games can be classified into two types. One is perfect information games, another one is imperfect information games. So, in perfect information games, both the players will have the complete information about the game, such as a tic-tac-toe and chess, etc. And imperfect information games are those in which players do not have the complete information about the game, such as cards and dice, etc. Perfect information games, imperfect information, where perfect information games have the complete information about the game, both the players, and imperfect games having only the certain knowledge about the game. It doesn't have the complete information about the game. Okay, game problem versus state space problem. In previous sessions, we have already seen the state space problem where all the possible states will be placed into the state space problem. So here, the state space problem contains the states, rules, goals, start state, goal state, and certain rules to reach from the start state to goal state. In such a way, the game problems also contains the legal board positions, legal moves, and winning positions. So if you take the chess, there are some positions which we will play the horse or soldiers or king or queen. Next, there are some legal moves. Only horse can move in the L shape like that. It have some legal moves and winning positions. The winning positions such as win or lose or draw the game. Next, here the game begins from a specified initial state and ends in a position declared loss or draw or win. A game tree is an explicit representation of all possible plays of the game. The root node is an initial position. Its successors are the positions that the first player can reach in one move. There are successor or position resulting from the second player moves. For example, if you start any game, for example chess, you need to move the first player, for example A and B. The A will play first, followed by B and again A. So both the players will play the game such a way that the individual has to win the game. A will play such a way that A has to win. B will play the game such a way that B has to win. So both the players will minimize the opponent to win, opponent to lose, such a way that so A can win or B can win. Okay, so terminal leaf nodes are represented by win, loss or draw. At last, A either can win, lose or draw. Either B can win, lose or draw. Next, here the philosophy of the game theory is minimizing the maximum possible loss and maximizing the minimum gain. The game theory is based on the philosophy of minimizing the maximum possible loss and maximizing the minimum gain. Okay, in game playing involves computers. One player is assumed to be the computer while the other is a human being. So here in the game playing there are two nodes. One is a max and another one is min. Max node will try to maximize its own game while minimizing the opponent's game. And either of two players, max and min, can play as the first player. Either max can play or min can play the first. Okay, the next one is status labeling procedure in the game tree. So there is a game tree For example, it will start like this, and here it will go, here it will go, here it will go. At last it is a leaf nodes which is declared as a win, loss, win, draw, like that it is declared. Okay, so we need to label the each node such a way that it leads to the root. That is a status labeling procedure, which will be the backtracking to one non-terminal to another non-terminal such a way that it will leads to the root node, and it will be decided node which player won that game. Okay, so the first one, if J is a non-terminal node at max point. For example, here max will play first, for example, later min, alternatively the players will play the game. After that again max, again min. Okay, such a way that the game tree will be formed. At last, there is a leaf nodes or terminal nodes. Based upon these leaf nodes or terminal nodes, which player is playing, in such a way the labeling procedure will be happen. So let's see the first one. When max is playing and it is the non-terminal node of the max, so the status labeling is if any one of J's successor is a win. For example, this one is the max point, and here one win, another one is loss. At max point, the J, if it is a J node, the successors of J, if any one of the successor is win, automatically it is win. If all the successors of the J successor nodes are loss, then only it is loss. If any successor is a draw and none of the one successor is win, for example, here it is a loss, then it will choose the draw. Let try to understand. If at a max point and the successors are win, loss, if any one of the successor is win, then it will pick up the win. If all the successors are loss, then it will be loss. If any one of the successor is draw and none of the successor is win, then it will choose the draw. Let's check. Win. When it will be win, if any of J successor is a win, loss. If all J successors are loss, draw. If any of J successor is a draw and none is a win, then it will choose the draw. Let's check the min node at non-terminal node. For example, it is a min point. Okay, this is the node which contains the loss, win, then it will choose the loss. So if all J successors are win, then only it will choose the win. If any of J successor is loss, then it will choose the loss. Means it will take the minimum value, so that max will take the out of these values only. Okay, the same, if any successor is draw and none is loss, then it will choose the draw only. Okay, try to understand. The first one, win. If all J successors are win, then it is win. If any of J successor is loss, then it will choose the loss. If any of J successor is a draw and none is a loss, then it will choose the draw. Okay, that is the status labeling procedure at max level and min level. Next, let's understand the complete game tree of when the max plays the first. So I said the level is first max plays, followed by min, followed by max. Means alternatively the players will play the game. So the first, don't consider this labeling status. Just look at the max playing the first. Okay. And min play the game. Again max. let's understand. Win, loss, loss, loss. Same game tree I have redrawn here. Win, win, loss, win, draw, loss. Okay, let's check how it will be. So first it will start with the root node back propagating. It will backtrack and it will label the max node at a root level. So at a max point, this one is a max and this one is a min and this one is again max. At a terminal level it is min. Okay, so here max first. There are two successors are there. If any one of the successor is win, automatically it is win. And max level, all the successors are loss, then it is loss. Next, any one of the successor is win, then it is win. Max level, any one successor is win, win. Max, any one successor is win, then it is win. Any one successor is draw and none of the successors are win, then it is draw. Next again. So that's it. Okay, next at min level, here win and loss. So if any one successor is loss, then it will choose loss only. If all successors are win, then it will choose win. If any one successor is loss, here look at here, draw and win, then it will choose the draw only. So loss, win, draw. Next, at max point, if any one of the successor is win, then it will choose winning path. So the optimal path to the game tree of the max playing and max winning path is this one. Here both are winning only. Anyone can take. Okay, look at this one, winning path. So if it will follows this path, then max will win the game. Next, when min plays first the same game tree, then how it will be placed. So min playing first followed by max, min, max. So at max is the terminal level and these are the winning positions. So here at min level, if any one of the successor is lost, then it is loss. Look at here, only one successor, that is loss. And here there are two successor, one is loss, one is win, then it will choose loss only, the minimum value. And here all the successors are win, then it will be win. Next, if any one successor is lost, then it is loss. If all successors are win, then it is win. There are no other successors, only one successor, so it will choose that only. At max point, so here if all the successors are lost, then it is loss. If any one of the successor is win, then it is win. Look at here the same. So here also win. But whereas to min player, if any one of the successor is lost, then it is loss only. So at what point the max can win? At he plays first, then it is the optimal path to win the game by the max. Because here max will be the computer and min is the human. So the developers will write the program such a way that always max will win the game. The AI will win the game. When min will place the optimal, the max also will choose the optimal moves only to win the game. So let's try to understand this NIM game problem. So the NIM game was developed by Charles L. Boughton of Harvard University at 901. So the game basically, there is a pile of matchsticks which will be at one time the matchsticks will be taken, half of the matchsticks. For example, there are 7 matchsticks. Then the player can take only half of the matchsticks. So half of the matchsticks means 3.5. So we can't take 3.5. We can take only 3. So the player can take 1 matchstick, 2 matchsticks, or 3 matchsticks. He can't take the more than 3 matchsticks. And the condition here is whoever takes the last matchsticks loses the game. So here the status labeling will be applied according to the max point of view. Try to understand here. When min at a min level, min is picking the last matchstick. So min is the loser. According to max point of view, it is win. Max is win and min is lose. When max is picking the last matchstick, according to max point, it is loss only. According to min point, if min will take the last matchstick, then max point of view it will be win. And according to the max point of view, when max taking the last matchstick, then he will be the loser. Okay. So there is a single pile of matchsticks, means a group of matchsticks, and 2 players. Moves are made by the alternatively. In a move, each player can pick up a maximum of half of the number of matchsticks. Whoever takes the last matchstick loses. Let us consider the single pile of 7 matchsticks to understand this game. Okay, so the convention of used for drawing game tree is that node contain the total number of matchsticks in the pile and labeled win-loss accordance with the status labeling procedure. Already we have seen that status labeling procedure. The player who has to pick the last sticks loses. If a single stick is left at a max level, then the rule of the game, max node is assigned status L. Whereas if one stick is left at the min level, then W is assigned to min node as a max wins. The label L or W have been assigned from max point of view at the leaf nodes. Arcs carry the number of sticks to be removed. Dotted lines show the propagation of the status. Let's see. The complete game tree for NIM with max playing. First, it is as follows. So here, the 7 matchsticks. Okay, so don't go with the win W. Just look at the matchsticks only. First, max playing first, followed by min, max, until it reaches the terminal node. Okay, here 7. So half of the maximum of half of the matchsticks. So here 7 means 3. So the max can pick up 1, 2 or 3 only. Next, at a min level, 7 minus 1, 6, 7 minus 2, 5, 7 minus 3, 4. So, out of the 6, the maximum of half of the matchsticks are 1, 2, 3. From 5 also 1, 2. From 4, 1, 2. Next at max level. So, in this procedure, from the root node to the terminal node, it will reaches the like that. 7 minus 1, 6, 6 minus 1, 5, 5 minus 1, 4, 4 minus 1, 3, 3 minus 1, 2, 2 minus 1, 1. So at last, at the max point, the max is picking the last matchstick. So according to max point, it is loss. Next, at the min point, look at here, there are another possibilities also. At the min point, the last matchstick is picking by the min. So here, according to the max point, it is the winning position of the max. Let's look at another one. At a max level, the last matchstick is taking by the max. So it is loss. The same way, here min is taking the last matchstick. According to the max point, it is win. So based upon this, so let's look at one by one. So here, winning position at a min level, at a max level. If all the success, if any one successor is win, then it is win. Next, from this, there is another one also there. Let's draw quickly. 7, 1, 2, 3. Max level. Min point. 6, 3, 5, 4. Next again. 1, 2, 3. So 5 minus 1, 4. 6 minus 2, 4. So 1, 2. 4 minus 1, 2, 1, 1, 2. 6 minus 1, 5, 6 minus 2, 4, 6 minus 3, 3, 4 minus 2, 2. Next, max level, 1, 2, min level, 4 minus 1, 3, 4 minus 2, 2, 3 minus 1, 2, 2 minus 1, 1. So 5 minus 1, 4, 5 minus 2, 3, 4 minus 1, 3, 4 minus 2, 2, 3 minus 1, 2, 2 minus 1, 1, and again here also 1, 2, 1, 2. At max point, 4 minus 1, 3, 3 minus 2, 1, 3 minus 1, 2, 4 minus 2, 2, 2 minus 1, 1. 3 minus 1, min point, 2, 1, 1 at max point. Okay, so at a max taking the last matchstick, loss, min taking the last matchstick, win, max taking the last matchstick, loss, min taking the last matchstick, win. Okay, now at a max level, max point of view, all, if any one successor is win, win. Okay, now to consider the next level, here we need to have one more successor. So we'll start from here. Max, lose, min, lose only. Okay, next, at a max point, all the successors are lost, then it is loss. Next here, min point, win, max also win. Okay, next, at a min level, the successors are loss, win, so it will take a loss, and here win, so it will take win, and here loss, win. Next, at a fifth node, loss, win, so it will take win because it is a max, and at a fourth node, win, loss, it will take win only, look at here, and 3, the loss, so it will take all the successor loss, so it is take a loss, and here win. Next, at a sixth node, win, win, loss, so it will consider loss. At a fifth node, win, loss, so it will take a loss only. At a fourth node, loss, win, so it will take loss, ultimately it will loss. When max plays first with the 7 matchsticks, it will be loss. Then look at a min plays first with the 7 matchsticks, then automatically it will win the game. The same procedure with the win game. Min, the last stick is taken by the min, so it is win. Max, any one of the successor is win, win. Next, min, if all the successors are win, then it is win. So if any successor is loss, loss, then max. Fourth node, win, loss, so it will pick the win only. And the third position, all the successors are loss, then it is loss, and here also win. Next, min, the similar procedure, and it is the winning optimal path, whatever is the dark lines are there. So here, look at here, all these are the, so if it will take this path, then it will be the optimal path when the max win the game. Okay, next, what are the strategies to win the game by the max player? There are 2 strategies are there. The first one is 2xi minus 1 plus 1, xi equal to, so these many sticks taken by the max, that the whatever left sticks are there, that will be left to take the min, so that it will be the winning strategy of the max. Okay, 2xi minus 1 plus 1, where x0 equal to 1. There is a sequence. If it is a x1 equal to 2, 1 minus 1 plus 1. So 2 into 1 plus 1, 3. The sequence is 1, 3. So here consider the n is a pile of matchsticks and these are the sequence. If this sequence is left to the min, then there is a chance to, the max definitely win the game. So this is the sequence. So the first I equal to 1 and I equal to x equal to 0, then it is 1. Next, when I equal to 1, 3 is the sequence. If x equal to 2, 2 into 2 minus 1 plus 1, 2 into 3 plus 1, 7. The next. So this is the one of the strategy. So there are n matchsticks in a pile. Then max can force a win by leaving m matchsticks for the min player to play. So using this strategy, leave these many sticks to take by the min player. Then there is a force to win the max player. Okay. So this is the sequence. For example, if n equal to 45, then we need to check the nearest value of the min. This 31 is the nearest one, closest one. So we need to 45 minus 31. The max has to take the 14 matchsticks. So the 31 matchsticks are left to play by the min, such a way that the max can win the game. The another strategy is, for example, there are 13 matchsticks are there, means n equal to 13. So how many matchsticks need to left by the max? So here there is another strategy. Convert this 13 into binary form. Next, remove this one and add and 0, 1, 0, 1 plus 0, 0, 1. Then it is 0, 1, 1, 0, which is a decimal form of 6. 13 minus 6, it is 7. So the max has to pick the 6 matchsticks, so that 7 matchsticks will left to the min to play the game. This is the sequence value. So in this sequence, whatever matchsticks will left to play by the min, then there is a chance to win the game by the max. Okay, this is another strategy. These are the two strategies. Okay, so here there are 4 cases are there when max plays the first, min play the first. So the first one is max is the first player. The second case is max is the second player. And when it is max is the first player and the initial matchsticks are not in the sequence. And the second, max is the second player and initially there are, these are the sequence of matchsticks. The n is from the sequence. So when the max will win the game, because we are writing the program such a way that max has to win, because max is the AI or computer. Okay, so validity of cases for winning of max player. Case 1, max is the first player and initially there are n not belongs to. So we need to take out of these values, for example 8, 9, like that, out of these sequence. Consider of a pile of 29 matchsticks and let max be the first player. The complete game tree will be shown in the next slide. Look at here, 29, and we need to pick the values. Max is the first player. Which one is the nearest value for 29? 15. So we can't take 31 because it is the highest value. We need to take the less value than this n. So here we have taken 14 values. We need to leave the 15, the sequence of these values. Okay, when we left this sequence, then the max will win the game. Okay, so if you take, so 15 is left, then automatically the same we have seen the before the game tree. 7 will be the min place the first with the 7 matchsticks. We have seen already the game tree. Okay, so automatically the max will win the game. Look at here. Whatever winning positions are there, we have taken only those values. Here we have not run all the complete game tree. So which strategy will win the max? Then we have taken only that one. If max is the first player and n not belongs to this sequence, then max will always win. So validity of case 1 example for n equal to 29 and m should be this sequence. 15 is there, next 7 is there, next 3 is there, last 1. Okay. Next case 2 is the second player and initially there are n. So max is the second player, min is the first player and n the first pile of sticks belongs to this sequence. So it can be 7 or it can be 15. So here we have taken 15 as the example. Let's see. So 15. Min is 15. So max will take the sticks next level and 7. When min plays at 7, we have already seen the game tree. So always the max will win the game. Next, other two cases. Case 3. If max is the first player and n belongs to, means initial matchsticks are the sequence. And the next case 3. Case 4. If max is the second player and n not belongs to the sequence. Let's see. Here 15 we have taken max is the first player, 15 is in the sequence. So we can't go with the 7 as the max level, then it will win the game. Look at here, 15, the same. From the 15, 7 till 7. So 1, 2, 3, 14, 13, 12, 11, 10, 9, 8. We are not going with the 7. When we go with the 7, at the min level, it will be win. At the max level, look at here, max. Except 7, pick up the sticks in such a way that 7 sticks are left to play by the min. Then only the max will win the game. If you take a 7, then it is a lost the game. It will lose the game. So, except this 7, we need to play at the max level. And 7 sticks has to left to play by the min, so that the max will win the game. Next, fourth one. 7 matchsticks at a max level. And here, except 3. If you take 3, then it is the loss. If you are accept this 3, then it is winning the game by the max. Okay. So, in this session, we have seen the game playing, one of the major topic. So, in this game playing, there are 2 players or 2 teams will play the, generally will play the game. So, here we have taken 2-player game and then the nodes are max and min. The max will be treated as a AI or computer and min is the human being. And here we have seen the NIM game problem using minimax algorithm, and in this we have already seen the status labeling procedure, and we have covered examples also, and we have seen the cases also. There are 4 cases. When min plays first, max plays first, the sequence, when n is the initial matchsticks, m is the max. After taking the matchsticks, whatever left to the min, those are considered as m, and this is the sequence 1, 3, 7, 15, 31 and 63, etc. So if you leave these sticks to min to play, then the max always win the game. Okay, in next session we'll see the alpha beta proving. Minimax algorithm with alpha beta. Thank you.